Hello there. In this lesson, we're going to learn about how the mole concept can be used with chemical reactions to determine quantities at the beginning and at the end of reactions. The fancy word for that is stoichiometry, and there's a little phonetic spelling for you, the stoichiometry. All right, let's get going. So everybody's already familiar with balancing equations, and you'd see like two oxygens on the left here, and you'd add a coefficient so that it balances out on the right, and then you see you got 2 times 2, that's 4 hydrogens on the right. You added 2 over here, so it's all balanced on the left. So in the end, in your head, you can kind of imagine yourself having 2 molecules of this hydrogen molecule, and then 1 molecule of oxygen, and together they could form 2 molecules of water. But that's like ridiculously tiny. There's no way you would ever be able to isolate 2 molecules of hydrogen and have them bump into an oxygen molecule in isolation away from everything else. However, we know that since this is a ratio, we can scale it up and it'll apply for 2 moles of hydrogen. Now that's a giant number of hydrogens, but it's an equivalent number to the 2 moles of the water that you would form as well. And so the mole concept can be applied using the coefficients from a balanced equation, just as we used it for formulas. So instead of just thinking of these numbers, the coefficients from a balanced equation, as just quantities of individual particles, you can think of them as moles, as equivalent quantities of a large number of particles, which is more practical and also measurable. Because if we have 2 moles of hydrogen, that's something we can measure. 2 atoms or molecules of hydrogen, not so much. So that mole ratio, the 2 to 1 to 2, is something you can use to interchange or to convert between different quantities used in a chemical reaction. So let's use an example here. We got 5 moles of hydrogen used up. How many moles of oxygen are consumed? And again, factor label method is great for keeping all this stuff organized. So we are looking for moles of oxygen that's consumed, and we are starting with 5.0 moles of hydrogen that are also being consumed. And so all you need to do is use the ratio from the balanced equation, 2 moles of hydrogen from the equation, there it is there, the 2, and 1 mole of oxygen from the equation, there it is there. And you see the moles of hydrogen cancel out. 5 times 1 divided by 2 is 2.5 moles of oxygen will be also used at the same time. It works the same way when you work across the equation as well. Both of hydrogen and oxygen are both reactants, but it works as well when you're talking about products. So it says if 5 moles of oxygen are consumed, how many moles of water are produced? So we're looking for moles of water produced, and we are starting with 5 moles of oxygen this time. And so again, you just use that coefficient ratio from the balanced equation, 2 to 1. We're going to have 1 mole of oxygen to 2 moles of water, and those quantities will cancel out, and we'll end up with 10 moles of water. So stoichiometry involves using those mole conversions from earlier, along with this new concept of a mole ratio from a balanced equation, in order to work out quantities within a chemical reaction. And there's 3 steps that you're going to follow in order to do that. First off, whatever measurement you have or are given, you're going to convert that into moles. So that's step 1. And then once you have moles of a measured value or a quantity in the reaction, you're going to use that mole ratio to convert to moles of the thing that you want, your target. So that's step 2. Once you have the moles of your target, then you might have to convert out of moles, because you might not be interested in how many moles of, say, a product you're going to get. You might want to know how many liters or how many grams, which is a measurable thing. And so that last step is to convert into the units that you want to end up with in the end. So let's give it a try. So here is a simple stoichiometry problem. We want to know what mass of oxygen is going to get used up while reacting with 5 grams of hydrogen. So we're given the 5 grams of the hydrogen, and we're curious about how many grams of oxygen are going to be needed to react with it. So what we do is we'll follow the same factor label method process. We're looking for the mass of oxygen, so we'll write that down first. So the mass of O2, and we are given 5.0 grams of hydrogen. So the first step is to convert from whatever value you're given into moles. And we know that hydrogen is 2 grams for every mole. And so that's step 1, convert into moles. Then step 2 is to use that mole ratio to go from the moles of the thing we have, which is hydrogen, to the moles of the thing that we want, which is the oxygen. So we want to go from moles of hydrogen to moles of oxygen. And the ratio from the balanced equation here is 2 to invisible 1. 1 to 2. There we go. Now the grams of the hydrogen have canceled out. The moles of the hydrogen have canceled out. Now we got moles of oxygen. So that was step 2. Step 3 is to convert from the moles of the target, the thing that we want, into the unit that we want. So it says what mass of oxygen. So we want to know how many grams of oxygen are going to be made. And for that, we can use our molar mass. So the molar mass of oxygen is 32 grams for every mole. And that will cancel out the moles of the oxygen and leave us with mass, which is what we were looking for in the first place. So with your calculator, you can work that out. So 5 divided by 2 divided by 2 times 32 equals 40. So you would need 40 grams of oxygen in order to react with 5 grams of hydrogen. So that sort of expands our mole map a little bit, because not only can you convert between moles of one thing into masses and particles and volumes and all that stuff, but you can also use chemical reactions and convert between moles of reactants to moles of products, or moles of one reactant to moles of another reactant. And so basically it's like sticking 2 mole maps together with this little link called the mole ratio in between that comes from a balanced equation. Alrighty, so let's try one where there's a little bit more variation. Again, we're looking for a mass of water. This is liquid water. Produced when 25 liters of oxygen is reacted at STP. Now, that's a gas, right? At STP. Okay, so we are looking for mass of H2O, and we are given 25 liters of oxygen gas. So we're starting here with a volume of a gas, and we want to convert into moles, then use the mole ratio, and then convert finally to a mass. So step 1, convert to moles. So the molar volume of any gas at STP is 22.4 liters per mole, and that'll convert us into moles of oxygen. The second step is for using the mole ratio. So we have the balanced equation here, and we want to go from moles of oxygen to water, and there's 1 mole of oxygen in the balanced equation for every 2 moles of water. So that's your mole ratio. That's step 2. Step 3, since we're going to a mass, we're going to need the molar mass. For every 1 mole of water, there are 18 grams, because that's the molar mass of water. And you see, just as a double check, liters cancels out, moles of oxygen cancels out, moles of water cancels out, and you end up with grams, which is the unit of mass, which is what we're looking for. Okay, so let's bang it in our calculator and see what we end up with. 25 divided by 22.4 times 2 times 18 equals, and I got, ooh, look at that, 40 again. 40 grams of H2O. There, I hope that helps. Follow those steps and stoichiometry will be no problem.